Take a look at this. It's a handwritten digit, a simple 7. You recognize it instantly. But what does it mean for a computer to recognize the 7? How does it go from a jumble of pixels to the confident declaration, "That's a 7"? This question, seemingly simple, unlocks the fundamental principles behind almost all modern AI, including the powerful large language models that are transforming how we interact with information and even create study tools powered by AI. In this series, we're peeling back the layers of these incredible systems. We're not just learning what they do, but how they do it, starting with the very basics. And our journey begins with this humble handwritten 7. Before a computer can recognize anything, it first needs to see it. For us, seeing is natural. For a computer, an image is just a grid of numbers. Imagine our 7 laid out on a tiny grid, say, 28 by 28 pixels. Each of these pixels can be assigned a number, representing its brightness or intensity. For simplicity, let's say 0 for pure white and 1 for pure black, with shades of gray in between. So, our 7 becomes a long list of 784 numbers. Now, how do we get from these 784 numbers to the answer, "It's a 7"? We need a way to process this information, to find patterns. This is where the concept of a neuron comes in. Think of a neuron as a tiny decision maker. It takes in several inputs, weighs their importance, sums them up, and then decides whether to fire or not. But why do we need to weigh inputs? Imagine you're trying to detect if there's a vertical line in a small section of our 7. Some pixels are more important for this than others. The pixels on the line should contribute strongly, while pixels off the line should contribute less, or even negatively. These weights are just numbers. A large positive weight means that pixel is very important for this neuron's decision. A large negative weight means that pixel's presence discourages the neuron from firing. And a weight near 0 means that pixel doesn't matter much to this particular neuron. So, each input pixel's value is multiplied by its corresponding weight. Then, all these weighted inputs are summed up. This gives us a single number, representing the total evidence for whatever pattern this neuron is looking for. But there's one more piece, the bias. Why do we need a bias? Imagine our neuron is trying to detect a very faint vertical line. Even if all the relevant pixels have small values, we might still want the neuron to activate. The bias is like a baseline level of activation, an extra push or pull, independent of the inputs. It allows the neuron to shift its decision threshold. A positive bias makes it easier for the neuron to fire, a negative bias makes it harder. So, the neuron's raw output is the sum of all weighted inputs, plus the bias. This is often called the preactivation. But this sum can be any number, positive or negative, very large or very small. We need to squash this number into a more meaningful range, typically between 0 and 1, or -1 and 1. This is where the activation function comes in. Why do we need it? Without it, our network would just be a series of linear operations, no matter how many layers we added. The activation function introduces nonlinearity, allowing the network to learn complex, nonlinear relationships in the data. It's what gives neural networks their power to model intricate patterns. For our example, let's use a simple sigmoid function, which squashes any input into a value between 0 and 1. So, to recap, a neuron takes inputs, multiplies them by ndlt, span style equals color green, and gt, weights ndlt slash span and gt, adds a ndlt, span style equals color yellow, and gt, bias ndlt slash span and gt, and then passes the result through an ndlt, span style equals color purple, and gt, activation function ndlt slash span and gt, to produce an output. This output is a single number, representing how strongly this neuron believes it has found its specific pattern. But a single neuron can only detect one simple pattern. To recognize a complex digit like 7, we need many neurons working together. This brings us to the concept of layers. Why layers? Think of it like this: the first layer of neurons might specialize in detecting very basic features, like horizontal edges, vertical edges, or diagonal lines in different parts of the image. Then, a second layer of neurons can take the outputs of these first-layer neurons as their inputs. These second-layer neurons can combine the basic edges to detect more complex shapes, like corners, curves, or small loops. This hierarchical processing is crucial. Each layer builds upon the features learned by the previous one, gradually extracting more abstract and meaningful representations of the input. Finally, we have an output layer. For our digit recognition task, this layer will have 10 neurons, one for each digit from 0 to 9. The output of each of these 10 neurons will tell us how strongly the network believes the input image corresponds to that specific digit. The neuron with the highest output value is the network's prediction. So, how does the network learn these weights and biases? Initially, they're just random numbers. The network makes terrible predictions. But through a process called training, it gradually adjusts these weights and biases. It's like a sculptor refining their work. They chip away, adjust, and refine until the sculpture perfectly matches their vision. Similarly, the network adjusts its internal parameters until it can accurately map input images to their correct digit labels. Imagine trying to do this by hand. For each of the 784 pixels, you'd have to decide its importance for detecting a 0, then a 1, then a 2, and so on, for every possible feature. It would be an impossible task. But with this layered structure of interconnected neurons, each learning to detect specific patterns, the network collectively develops an incredibly sophisticated understanding of what makes a 7 a 7. It's an emergent property, a complex intelligence arising from simple, repeated operations. This fundamental architecture, inputs, weighted sums, biases, activation functions, and layers, is the bedrock upon which all advanced AI, including the LLMs that power your study tools, is built. From recognizing a 7 to understanding complex human language, the core principles remain surprisingly similar. So, what did we learn today? First, images are just numbers. Computers see by interpreting grids of pixel values. Second, neurons are simple decision makers. They combine weighted inputs with a bias and an activation function to detect specific patterns. And third, layers allow for hierarchical feature extraction. Simple patterns combine into complex ones, enabling the network to recognize intricate objects like our handwritten 7. If this kind of deep understanding of how AI works is valuable to you, consider subscribing. In the next part, we'll explore how these foundational ideas scale up to process sequences, which is crucial for understanding how large language models work. One more thing for the curious.